Anybody here who managed to work a little on the data set? Okay, all right. So in that case, let's begin with the topics that we have for the week. So we're going to be discussing three models today, namely the voting classifier, the bagging, as well as random forest. So can someone tell me what bagging classifier is first? What do you all recollect about bagging classifier, either from MLT or what you might have seen in MLT? Any answers? What bagging classifier does?
So bagging does ba- bagging first of all takes subset of data points and then uh, trains uh, weak learners parallelly and choose majority 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 votes for the final result, and as well it helps to reduce variance.
Okay, great. So you brought up a few points. So it trains multiple models on different subsets, and then it helps to reduce variance. Okay. So anybody else any other points about bagging? What do we do in case we don't have enough data points? What can we do? So when we are going to build different models, so I think Jan Prakash said that we'll be training multiple weak learners. So we'll need this data set to train multiple weak learners. So can someone give some more info on what exactly happens in the case of bagging? Whatever points you will recollect. Okay, all right. In that case, let's have a look at the documentation itself, and we'll go from there. So this is the page for bagging classifier in SQL. So it is called as an ensemble method. So can anybody tell what ensemble methods are? Any answers for
So
ensemble method? Yeah.
bagging and boosting, where we combine multiple models.
Okay. Where we combine multiple models. Any other models come under ensemble type?
So boosting,
Yes. Boosting, bagging, anything else?
ADA boost and gradient boost as well.
Okay. They are boosting variants, but are there any models that are not, say, of boosting type? You can actually see the names even there on the side here. So all these things that are mentioned here are ensemble methods. So today we'll be seeing bagging, we'll be seeing random forest, and then we'll be seeing voting. So ensemble methods, as we mentioned, is one where we combine multiple different models. And the general idea again is we can combine multiple models such that when we average it out later, we might have a better model. So that way we are reducing the variance. So specifically coming to bagging classifier, what it does is it is a meta estimator. So it is an ensemble meta estimator, meaning that it takes different Bayes models, and based on whatever predictions those Bayes models have done, we then aggregate it. Okay, so there's two parts. The first is we take random subsets, we fit Bayes classifiers on random subsets of the data, and then we aggregate the individual predictions to form a final prediction. Okay, so these are the two parts. And again, the advantage is that it reduces the variance, and it is done so by introducing some sort of randomization. Now, coming to why subsets of the original data set, because we want each of these weak learners that we build to learn as many different things as possible. So we want these weak learners to train on, say, separate parts of the data. It has to capture separate things. Again, we'll see it more when we look at the data set. If you'll recollect from this rainfall prediction data set, it had these multiple features. So it had wind speed, wind direction, cloud, humidity, So we hope that these different weak learners, when we train, they learn on these, they rely on these different features in different models, and they do some kind of performance. And then collectively, when we average it out, we are hoping that the overall this one turns out to be better. So this is a broad picture of what bagging is. And coming to different subsets of the data, since we are going to be building say many models, we might not always have the luxury of having that higher data set as well. So for that, what this does is a process called as bootstrapping. So in the case of bootstrapping, we have a data set. From that, we sample a portion of the data set, and specifically we sample it with replacement. So when we do it with replacement, this process is called as bagging. And then based on that, we can do, then next we again take another subset. So it's not necessary that the same points may come. So sometimes some points may come, sometimes it may not come. The exact details is, again, you can revisit MLT. The prof talks about what is the percentage of point, chance of a point being selected in each this bag and so on. Okay, so roughly this is what bagging classifier is. Coming to its parameters, it has a few important ones that we'll have a look at. So one is estimator. So by default, we tend to use the decision tree models, and which you can see here, the Bayes estimator if fit on random subset of the data. If none, then the Bayes estimator is a decision tree classifier. The next is N estimators, how many estimators you would like to use. So here we train 10 different weak learners and then combine them. And then comes max samples. This is how many points you want to take. So this is the number of samples to draw from X to train each Bayes estimator. So the idea is that we don't want the whole set of the points to be taken, which is why you can give some sort of value. So now in this one, X dot shape of 0 says how many rows are there. And if you give an integer specifically, say I have 20,000 samples, and if I give a value like 5,000 or something, each estimator will be trained with 5,000 samples. But if I give a float value, that is a value between 0 and 1, then it is going to multiply this particular value with whatever number of rows I have. So if I give 0.5, and if the number of rows I have, that is if X dot shape of 0 is 20,000, then it is going to do 0.5 into 20,000, giving me say some 10,000 values, and it is going to build on that. The next part is max features. How many features do you want to make use of to train each Bayes estimator? Usually it ends up making use of all of the features. Then is bootstrapping, whether you want to draw the samples with or without replacement. So in general, it's a good idea to use bootstrapping, and only if you have maybe a very large data set, you could probably choose to not bootstrap. And then this is again whether features are also to be drawn with replacement. We saw max samples here, and we saw max features. So features also whether we want to sample it with or without replacement. So the next one is OOB score, which is OOB stands for out of bag. So out of bag score is, it kind of tells, so we saw that we might take a subset of the data, and we are going to train a Bayes model on that. Now there are some points that are not chosen, right? So can we use that as sort of like a test set? So this is what this OOB score does. In a very vague sense, if we use bootstrap, all the points that are not selected can be used to kind of get a generalization error. So warm start is, again, we've seen this previously as well. If we use fit, and if we want to reuse whatever we have learned, we can use warm start equal to true. By default, it is false. N jobs is something more relevant when you can make use of multiple processors. And then we have random state and verbose. Random state is again for randomness. And from what we've discussed, there are a couple of things here. Primarily, it is which samples are taken and which features are taken here. So this is the random part that comes in this particular algorithm. Are the parameters okay? Any questions? So we discussed the bagging classifier, broadly speaking how it works and what its parameters are. Any questions on this? Okay, all right. So in that case, let's probably try out a model. How many of you have not seen this data? Can I get a show of hands? It could be either by yourself or in the previous sessions. Is there anybody who has not seen this data, the rainfall prediction data set? Okay, so in that case, I'm going to assume that you have seen this and directly go ahead to the model building part. So this was the data set we've been working on, and we have done some basic steps which we'll run again. This is the train.head, how many features are there, the first 5 rows for each of the features and so on. Let's go to where we stopped the last time. Okay, so we are done until here, feature importances. So I'm going to run those cells again until here. Okay, now let's try out the bagging model. We have called our train and this data as X train and Y train. Okay, so what was the score we had obtained from decision tree? Where is it? Okay, so with decision tree we had obtained accuracy of 0.79 on one of the models. Yeah, it was 0.79, and this time we see that we have definitely got a higher value, which is 0.83. Let me run the same model here as well, perhaps. Okay, so the decision tree model has given us 0.78, and we can see that the bagging classifier is already better at 0.83. So in practice, we might run this a couple more times with different samples and see overall if this particular model is doing better. Any questions on what we have done? Fairly straightforward, I hope.
Can you once summarize, sir, what we have done till now?
Okay, so do you recollect the data set that we've been working on?
Yes, sir.
Yes. Yes, Bhavana.
So my question regarding whenever we work on any data set, so there we work on each and every model and find which one is best.
Yeah, that is one of the things that we tend to do while working in practice. We try out different kinds of models.
Okay.
Yeah. So ideally, you would want to
But
try.
sir,
Yeah.
I read somewhere decision tree and bagging are almost similar, but
Mhm.
decision tree more robust than bagging.
Okay, so that might not entirely be true. So it is true that they are similar in the sense that bagging also makes use of weak learners where we generally tends to be decision trees.
Sir,
But
can you explain weak learners? That time I'm listening MLT, but I'm not understood what is meaning of weak learners. Means
okay,
those features which are not.
no. So weak learners are ones that generally don't tend to do that well. For example, now this is actually a weak learner. So this decision tree classifier that we see. So let us see if we can see the parameters of this. Uh, so let's do the parameters check first. Okay, this is anyway the default parameter. So we have had no depth for maximum depth was none, minimum sample split was 2, minimum sample leaf was 1. So we have allowed this model to overfit in some sense.
Hmm.
Okay. So this model to decision tree. So now this actually can be called as a weak classifier because this is not ideal. This is not the best. We have quickly built some model where we have allowed it to grow as much as it wants. Now that we also saw by score, right? The moment we come to bagging, there is a pretty significant increase from 0.78
Because
to
we are not
0.83.
giving any parameters in the
Correct. We are
decision.
not doing any parameter tuning, none of that. We are
Okay.
just building one decision tree as it is. We are allowing it to go to maximum depth. You recollect from the previous discussions, right? Allowing a decision tree to go to maximum depth, it causes it to overfit and all that. And in general, it's not that great a model. But we just need one model to be there quickly. So that way it's a weak learner. It's not something that necessarily separate things very well. But that is okay for us at this point. So you might also remember the idea of making use of decision stumps, wherein it's like very tiny decision trees, and it just takes one feature, yes or no, and we have one structure. So those are also very weak learners. So they don't capture, they are not good models basically, but we can do it quickly, and that way we can do multiple different variants of it, and then we can combine them. So that is the difference that is happening in bagging. So these models that we built quickly with decision trees, we are combining multiple of them so that the overall mistake made is averaged or rather reduced. Okay, something like that. Is that okay?
Nice.
And
So,
the
sir,
yeah.
whenever we work on any data set, so we use no without parameters. We try to every model without giving any parameter by default parameters like that,
Yeah, so you
or
can
we choose some parameters
right.
own.
So in general, the approach would be that you can start with the default parameters, and you can see how the model is performing. And once you see that, you can start adjusting the parameters. You can do hyperparameter tuning, and in hyperparameter tuning, what values to take, it comes either a bit with practice or with some domain knowledge. If you have done things previously, you might roughly know what might be some good values to try out. So now you did this decision tree model and say you found out that it is, you can do the cross validation and all that. And if you found that your model is overfitting, in that case you can just slightly increase the max depth. So we can give it a value. So maybe I'll give it the value, say 5. So let's see if it changes anything. Yeah, you can see from 0.78 it went to 0.82, right?
Hmm.
So now this is not always necessary, so it needn't have gone up. But the general idea is that the decision tree with the base sort of parameters is allowed to grow as much as it wants. We saw, I think, one example of a tree here, and here again we had given a max depth. But if I did not give a max depth here, then it would grow a lot. So maybe let's view that as well. So this way you start getting an intuition as to what is good and what is not. And if it overfits, I can start tweaking some parameters to slightly change it. Now let's see the
So, sir, every time we use, after that we use the hyperparameter tuning. That's we
Yeah, once
find
you
this
use the
one is best.
hyperparameter tuning, you might kind of, can you see this tree? So this
Yes.
is the decision tree without setting any parameters. This is left to its default parameters. There are multiple problems with this. One is there's a good chance it is overfitting. The second is it also becomes harder to interpret. So if you recollect from our discussion during decision trees, I had said that one of the main advantages that decision trees gives is how simple it is and how easy it is to understand.
Yes, sir.
But now that part is lost with this. So which is why we can, tend to give it a depth and we can start analyzing things. So that way we can then whatever we have done now, we can build things on that. So now I changed it back to max depth as 2. And now here I'm roughly getting an idea. Okay, it looks like cloud is an important feature. And yeah, maybe I have to increase further to see a couple more features. But roughly we start getting some idea now. So then we can even see how bagging has done, how the other algorithms have done. Do we find any strong correlation between the model performances and so on? Okay.
Okay.
So yeah, to overall, I would say start with the base models, then try out a set of hyperparameter tuning, then go with the test other models. For example, in general, you will find that these models like random forest or boosting tend to perform better than the basic decision tree models. As a matter of fact, some of the better performing models in classical machine learning are things like XGBoost and LightGBM, which it's not specifically covered here, but you'll be seeing more of it when you try out your project. Okay, so that way, if you have your data set and if you feel it is complex, if you want to go for explanation, you can try the linear models or decision trees. But if you want to go more towards a better score, if your only objective is to get a high performing model, it might be better to directly start trying out the ensemble methods. Okay, so that will be your approach. You try out ensemble method. If you get a good enough score, try hyperparameter tuning. If you feel that it is improving, then you can kind of have that, try again, go back and do some feature engineering. So it will be an iterative process. Okay, so that is how it is. Coming back to it, so decision tree with the base one, we saw it gave a 0.79 score. Now with bagging, we got 0.83. Let's see if we can change some of the parameters in bagging as well. Maybe let's have these. So I'm going to remove these things. I'll give random state as 42. Bootstrap is true. Bootstrap features also, let's try with true. Max samples, let's go with say 0.8. Max features, again 0.8. Let's actually leave it at 1. And let's increase the number of estimators. So this time 20 models will be fit. Yeah, you can see the score has gone quite down. So it's not necessary that if we change these things, it is going to improve the performance. But you can keep trying out these different things and see whether they have an impact. Okay, so Bootstrap features didn't change things much. Max samples, let me go back to its default. It is still pretty bad. Number of estimators, let us go to 10. Okay, it actually continues to go down. So in that case, previously we might just have gotten lucky with the score. So when we had not given anything, did this and this. Yeah, so in this probably we just got lucky with it. and we can try out different random states. Okay, now it's 0.84. 0.81. Okay, it's roughly giving above 0.8. But then with this base, whatever you have, you can include the base parameters and then do some hyperparameter tuning. Is that okay? I mean, let's bring up the code that we had used previously itself. Let's include model 3 and let's see if we can give n estimators will be one of them. Let's actually just start with this. Okay, so here we are performing research CV. So now you can see the model is training with different number of estimators. So the first is with just 5 and you can see scores like 0.84, 0.86, 0.871. Here one of them is 0.880. So this way on running this model we are going to get our best parameters. So then we can just do score. Okay, and this time we got again, after hyperparameter tuning, the score has slightly increased. It has gone from 0.83 it was when we used without any random state. Here it was 0.8424, here it is 0.8493. That way a slight increase. So any question on this particular model? Bagging classifier? Okay, all right. So,
Yes, sir.
yeah. So next in that case, let's go with the random forest classifier. So anybody, any idea as to what random forest classifier is? What does it do? Okay. So coming to random forest classifier, it is again, once again, it is a meta estimator that fits a number of decision trees on various subsamples of the data set and so on. So the difference is that here, in the case of bagging, it was primarily, we took samples of the data set, trained different weak learners of, and the default one was decision tree, and then we aggregated it. Here, it is going to start with decision tree itself. So it is going to make use of decision tree, and all the parameters corresponding to that can be treated as hyperparameters. So it is a collection of these very weak decision trees that is then combined to give out a good model. So few of these parameters you all will have already seen, things like criterion, max depth, minimum sample split, minimum samples leaf, and so on. The different ones, again, you have seen Bootstrap, OOB score, and warm start. These are again similar to what we have already seen. The number of estimators, once again, by default, it is 100 in this particular one. So we'll directly get into random forest classifier as well. Call it model 4. So in general, when you do hyperparameter tuning on something like random forest classifier, it might take some more time than other models, and that is totally fine. Okay, once again we've got a score of 0.84 with this as well, which is similar to this one. Maybe we can check things like the classification report. Let's first do the confusion matrix. Takes in white test and white bread. So let's just pass those. So So this is for the previous hyperparameter tuned bagging model. I'm just trying to print out the confusion matrix. Okay, so this is what confusion matrix for bagging looks like. And since we have a similar score, it will be interesting to see how it does for the random forest model. So let's just run the same thing for random forest model as well. Seventy-one, 48, 18, 301. Okay, it is slightly different, but we can see for the most part the true positives and true negatives, whichever we take as a class, it is quite similar in performance, and the ones that are predicted incorrectly, it's 40 something here and 20 something here, which is again 40 something here and close to 20 here. So this way it will be interesting to see why the model has misclassified these particular points, and you can do a comparison like which models are misclassifying which ones and so on. Okay. Any doubts with this about the analysis also? Okay, all right. So in general, once you train any model, you need to make an analysis of the results that you get. So in the last week, we saw things like making use of the classification report and so on. Another one to do is once you build a model, see which points have been misclassified and see if you can find a reason as to why it has done poorly. Okay, so the final model that we are going to cover today is called as the voting classifier. Of course, for both bagging as well as random forest, it has its regressor version, which will be similar, just that instead of using the classification model as your base estimator, you are going to be using a regressor. Now, can someone tell me anything about voting classifier? What do you all know about voting classifier? How does it work? Any points about it? No answers, no idea about voting classifier. So voting classifier is, as the name suggests, it is based on vote that is put forth by different estimators. By estimators, I mean different models. So rather than relying on the performance of one model, you are going to train multiple models, and collectively based on their performance, you are going to make a prediction. So that is why voting classifier takes in estimators as one parameter. Then it has something called as hard and soft voting, which is whether you want to take majority as it is, or do you want to sort of give it a probability like thing. Then there is weights, and then there is flattened transform. We'll come to these. So firstly, if you give voting as hard, that means it is majority rule voting. If it is soft, it predicts class level based on the maximum of predicted probability. So which is, you can give it different values. So here you can see here, which has the option weights. So it will tell you which one you want, what is the weight that you want to give before you do the soft voting. So now I have say 3 models, and I feel my first model might be say just decision tree. The second one might be something like perceptron, and the third one might be say random forest. And I have a feeling that I have to give more the weight of the random forest if it should be higher. Then I can simply give random forest as say 0.5 and the other two as 0.25, 0.25. Then whatever value they predict, say my SVM and say my perceptron and decision tree predict label 0, whereas random forest predicts 1. So then depending on what we have given as a probability here, it is going to multiply those with them and finally take the maximum value out of it. So if this is a little confusing, let's actually just directly see it a bit in practice. Let's import it. So here again the same thing is mentioned. Let's just take the core snippet from here. Okay, so what this has done is they have done. Okay, it's fine. We'll try out these models itself. Okay, so let's go over this code. So they have used 3 different models. They have used logistic regression, random forest, and Gaussian naive Bayes. They have called it CLF1, CLF2, and CLF3. So the dataset will run this dataset also once necessary. And based on what these 3 different models predict, we do a hard voting, which is we take the majority vote and then make the prediction on Y. So again, it's binary classification. There is class 1 and class 2. So let's run this. So the predictions given for the 6 points were 1, 1, 1 and 2, 2, 2. So let's individually see how these models have done. Let's do CLF1.fit x comma y. As you all can see, this is just a dummy example because it is predicting on the train data itself. CLF1.predict x. Okay, it predicted 1, 1, 1, 2, 2, 2. This is our first model. Let's just club this. And we'll do the same thing with our second model. It also predicted the same. What about our third model? Okay, it also predicted the same. So this is pretty useless to us. Since all 3 of them predicted the same thing, even if we were to take the majority, we'll just get the same value. Maybe, I don't know if one of them did differently. Okay, now we finally see a change. So I've slightly modified the data set. So I've changed the label of the second point to 2. And now you can see the first model says for the first point, the label should be 2. This model and this model says 1. CLF 2 and 3. But the majority is taken, and since 1 is the majority, the assigned label is 1. For the second point, this model predicts 1, this model predicts 2, this model predicts 1. Again, 1 is the majority, so 1 goes here. For the third one, we have 1, 1, 1. So since there is, for the rest of the 4 points, all of them are in consensus. So that is why it just ends up giving the value as it is. Is it okay? Is this tiny example clear? If it's not, I can repeat in more detail because this is all there is in voting classifier. If you get this, you'll understand it even in the other cases.
So it means a voting classifier use those model.
Yeah, it internally uses those 3 models, their predictions it takes, and then depending on what kind of voting we take, it takes either a majority or it takes the probability and then takes the value. Is that okay?
If we using voting is equal to hard, if we doing voting is equal to soft, then
Yeah. So if we do voting equal to soft, let's just run it. So first you will see that by default, even if voting is soft, it will end up. I mean, these values won't change anyway. CLF 1, 2, 3's predictions will remain the same. But it's like this. Now, what do we see here? So this model predicted 2, this model predicted 1, this model predicted 1. So what should the majority be if the voting was hard? So you have 3 models. So first one predicted 2, the other 2 predicted 1. If with hard voting, what will the answer be? Should it be 1 or 2?
1.
It should be 1, right? So let's try and change it here. So we have weights. See the syntax for it. So now I've run this, and can you see the? Okay, it is still. Yeah, I think it should be like this. 3, 1. So these weights tend to control how much this has to be given to the other guys. Now I'm trying to sort of cheat my way into giving a high probability for the first one to change this. Okay, what was it? What was the class probability for this? Okay, it was only 0.517, so I might have to make this very high. Okay. So yeah, this, like I said, it's a bit of a cheating that we have done. We have 3 models, and I knew that the first model is predicting 2, whereas the other 2 guys are predicting 1. So I've simply increased the weight of the first model so much that no matter what the other guys predict, it will always dictate what value it takes. Is that okay? So while using the soft weighting and by passing weights, it told what is the sort of weight I have to use to multiply to the probability before I take an average. So here there was different averages. So we saw this when we did the predict proba. So for the first data point, it was like 0.517, but now we are weighting it so much that we have made it. We have made sure that this one is dominating the others. Okay, so you can try out taking a smaller example and working with the pen and paper, and that should make things clearer. Run the same code on a Colab file and try it out on your own. Okay, so this way, by weighting things, we can say which one do you want to give more emphasis to. So in this one, let's just change the data set to what we have. I'll just copy this here.
So can you again explain weights part? I'm confusing. Weight means you give the three types of weights.
Yeah, so weights, first let's come back to this SQL and documentation.
Yes.
So weights takes an array of shape n classifiers, that is whatever number of classifiers you have, you want to give that many values of weights. So if it is hard voting, the sequences of weights will weight the occurrence of the predicted class label. So if your model 1, okay, let's do it with the case of hard voting. So first everything let it have equal weight. So it predicted 1 1 1 2 2 2. So this is because the models we have done 2 1 1. This, by the way, this is clear, right? There are 6 values in training data, hence we are getting these 6 values. So for the first point, the first model predicted 2, the other two guys predicted 1. But because of majority, it became 1. So now let me increase this to 2. So still it is not sufficient. Now let me increase this to 3. So the moment I increase this to 3, so now this guy's prediction was 2. But now because I'm weighting it, so this guy's prediction has more value. So here what this is saying is, weight the occurrence of the predicted label. So now this guy says once, these two says 2. But then because the weightage of this guy is 3, so it accounts for this being present more number of times. Even though it is present once, it will now say that it is present 3 times. Is that okay?
Yeah, yes.
So if I change this back, if I make this guy also 3, now it will go back to 1 1 1 2 2 2. So previously all of them had one say. So this guy said my one candidate is 1. This guy said mine also one candidate is 1. Mine one candidate is 2. So then we took majority, and because these two guys were 1, the value ended up being 1. But then we said my one candidate is 1, my one candidate is 1. But for this guy we said instead of 1, I'm sending 3 candidates. For all 3 guys the value is 2. So this way we now are looking at 5 values and taking a majority. Are you getting it?
No, sir. I'm still confused.
Okay. Yeah, so, okay, first can you tell me what voting classifier is doing when the voting style is hard? Have you understood that part?
No, sir.
Okay. So let's get rid of this weights for the time being. Okay, so we have these 6 data points.
Yes.
Minus 1, minus 1. So these 6 points, these are their 6 labels.
Yeah.
For simplicity, I'll change it all to 0, 1. So we have these 6 points, we have these 6 labels. And first, let us run these 3 models. We have logistic regression as one model. Let me remove this. Then we have a random forest classifier with 50 estimators, and we have a Gaussian naive Bayes. Okay, this is our model. It is called CLF1, CLF2, CLF3. So the first model predicted this as the labels for the 6 points. The original labels you can see are 1 0 1 0 0 0, but our logistic regression model told it to be 0 1 1 0 0 0. Is this okay?
Yes, sir.
Then we run the second model, which is random forest. This guy said 1 0 1 0 0 0.
Yes, sir.
Which actually happens to be what this guy also is saying, the original labels. So then we run the third one, which is Gaussian naive Bayes. It says 1 1 1 0 0 0.
Yes.
This is again not matching. There is one mistake.
Yes.
Now, instead of relying on one of these 3 models, so in practice we won't know the labels of the test data, right? At least we won't know it beforehand, right? Is that okay? The general way, we do the model training on training data, and then we check its performance on the test data, because we want it to generalize better on unseen data.
Yes.
Correct? So that way, even though this model has exactly matched it, in practice we have no way of knowing that this might be the case. So instead of relying on just one of these 3 models, we take a vote. Okay. So now my first point is -1 comma -1. Its original label is 1. But now instead of directly predicting based on one model, I'm going to say, okay, this is my model 1. My model 1 says the label for the first point is 0. The model 2 says the label for the first point is 1. And the model 3 says label for the first point is 1 again. So
Yes.
since we have two guys saying 1 and one guy saying 0, the majority being 1, we predicted it as 1.
Okay.
Okay. Coming to the second point, originally it was 0. But the first model said it is 1. Second model said it is 0. But the third guy also said it is 1. So now even though it is incorrect, because the majority is once again the label 1, it ends up being predicted 1.
Okay. Yes.
So hard voting part, is it clear?
Yes. Yes, sir.
Okay. So now what did I say? Everybody. So this guy says, okay, my. So let's come back to the first point. So this guy says my prediction is 0. These two guys said my prediction is 1. So far we were giving equal weightage to everybody. So whatever these three models said, if you say it is 0, you have one vote. This guy, if he says it is 1, okay, it is 1. So similarly, like one weight. But now here I can slightly change it. I'm going to make this 3. Okay. So when I make this 3, you can see there is a change that has happened. So
Yeah.
if I see just these three models, these two guys are saying 1, but even then my predicted label is 0. Because now what I'm doing is, whatever this first model is saying, I'm giving it more weight.
More weight means we give the weight is 3.
Yeah, I
So
gave the
how
weight
it
as.
work?
So what it means is, whatever prediction, if you are saying that it is 0, I will take it as though there are 3 zeros. 3 people saying 0.
Okay.
Okay, so now actually there are 3 models. But now I'm saying whatever this guy says, it is equivalent to 3 models predicting the same thing.
So that's why
Yeah, so it
weightage
is like
vote
3
is
people said 0 and 2 people said 1.
1.
So
So
now my
that
majority is
vote
again 0.
okay.
Now if I change this to this guy also being say 3, now it again goes back to 1. Because now this guy might have said 3 to be 0. But this guy said 3 is 1 and this is with weight 1, it is 1. So now there is 4 again. Is this making
That's
sense?
equal. Not, but it is not making sense. All these.
The weight part is not making sense, is it?
Hmm.
Okay, so in that case, in the Thursday session, I'll just first start with an example where I'll solve it with pen and paper. And then from there, I think we can go ahead. Okay.
Okay, sir.
So roughly, this is the idea. Instead of just listening to one model, we are going to be listening to multiple models. Is
Yeah.
this part a little confusing to anybody, to other students as well? Okay. So regardless, I think it will be better if I take an example. I'll do that in the Thursday session. We'll solve a small question on pen and paper and then come back. So roughly the idea that you need is, instead of relying on one model, I'm now taking the opinion of multiple models before I make my prediction. Okay.
Yes, sir.
Let's go back to hard voting. This time we'll go back to our original rainfall data set. So I'm going to pass in X train, Y train, and we'll do score X test, Y test. So there are 3 models. Those 3 are passed through the voting classifier. Based on whatever label they predict, the majority vote is taken, and that is used for prediction. And it says there's an error, which is from an extra. And this is fine. Where is the bracket extra? This is an extra bracket. Okay, the score is once again 0.8493. Let us print the confusion matrix. So we call this model ECLF1. Okay, once again we observe a similar performance. So ideally we want to see how we can improve this. Here now we can try out different model. So let's say from a scalar dot. Let's do some other models. Yes, 7. Okay, let's see if we can try this out. Instead of Gaussian naive Bayes, let's go with okay. Once again, it is similar performance.
So here we change some in ECLF voting classifier, the GNB, Gaussian naive Bayes. Okay.
So here, this
Yeah,
GNB
yeah.
is just like a label. It is like a
Okay,
name that is
okay.
given. The model in question will be based on this variable.
Yes, same.
Yeah. So we can even increase it. So we can keep say CLF3 as GNB, and here let's do this for CLF4. Let's do this as okay. So once again, the scores tend to remain the same, but now we are using 4 estimators. So in general, it might be a good practice to either use like
So
odd
in,
number of
this
estimators.
line, we cannot pass the fourth estimator voting
You are right.
classifier.
So I've not done that at all. Good catch. So that was mistake. So looking at HVC, CLF4. Okay, now we see a difference. The score has actually slightly gone down. So this way we can keep trying different combinations of models. And in general, it might be good to try out models that capture different things. So this way we can take a consensus, and based on that we are voting. Okay, is this?
Sir,
Yeah.
what should be a thought process to use the different model?
So in general, now ideally there is actually another model which is probably not explicitly covered. So it's called a stacking classifier. So stacking classifier also tends to do very well in that. And I would say in general, when you go with something like this, uh, go for different classes of models. So now this random forest, and you can try random forest is decision tree based. So maybe rather than going for another decision tree based like we did here, you would go with logistic regression. So in general, you tend to get an intuition. Like I said, you start with trying out different Bayes models, doing hyperparameter tuning, and so on. That way, when you try out these multiple different Bayes models, you know that some of them are obviously doing bad, and some of them are, okay, it is neither too great nor is it too bad. So that way, you can take a collection of these and then think about passing them in. At the end of the day, this entire process is going to be experimenting things and doing them iteratively. So based on that, I'd say you can try out different models, see whether they are collectively making mistakes on one particular set of data, like we saw here. So there is a good number of mistakes it is doing, wherein class 0 is misclassified as class 1. If you can see why it is specifically doing poorly on these points, and if you can find a model that tends to do well on this section of points, then maybe you can try and bring that in your setup. Is that okay?
Sir, my point is,
Mhm.
as we look into this, it looks like a hit and trial method. But
It
what
is.
is the thought process as you introduce this linear SVM?
Yeah.
Is there any thought process to introduce this linear SVM, or why not some other
Yeah,
things?
so
Or
you can
it
try out
is
different things. So for one, it will be a lot of hit and trial also. But the other thing, like I said, is what you'll initially do is now today we are discussing this particular method, so we directly came to this. Otherwise, you would have tried different methods, like you go on starting from say logistic regression, You can go for perceptron maybe. Then you have different variants of SVM. Then tree-based models. So all these guys, you once build a baseline model for all of them, and you see their performances. If there are ones that are doing evidently bad, then you can ignore them. But if there are ones that say multiple models are giving you, now this one gave a score of 0.83. Now if there are multiple models that are giving a score of say around 0.8 or something, then you can club those things together. So here I simply wanted to put out a different model and see how things change. But in practice, you try out all these different methods. You come here to classification models. So we'll learn classifiers. So here it shows you all the different methods. Yeah, so here you'll see the different methods. So linear models, there are things for classification. You have rich classification, and you have perceptron, you have SGD, which again takes in different ones, and then you have nearest neighbors. So k nearest neighbors classifier you can do, and then naive based classifiers, tree based models, ensemble based models. This way you do the base version of all of them, and you see what their performances are. Here we saw that random forest I think gave 0.84 or something, right? Yeah, random forest gave 0.84. So it's a good model to have. Along with it, I might not use another random forest instead or decision tree. Instead, I'll go for some other type of model. Is that okay? So something whose underlying working is different. That way you might want to take up a collection.
So from different class, if someone is giving the best score, that can be included here, right?
Yeah. So that's the thing. At the end of the day, again, it is going to be a voting thing, and we cannot say for this subset you use this model, for this subset you use this model. If we run it in this manner, at the end of the day, if you feel there is a significant difference in the two data sets, then you can train them separately. But again, that problem will happen if you find that one model, say this model 3 is doing well on certain parts of the classes. But how do you change it? So one thing to do is to assign weights, wherein you say you listen more to this model, but then it can perform poorly on another class, right? So how do you manage those things? So those are some problems you'll have to try and solve.
Oops, thank you.
Okay. So those were the three models I specifically wanted to cover in this session. Do you all have any questions on these?
Sir, there is a way to select best parameter, right? So similarly, is there a way to select the best base model here?
Not necessarily. So once again, it will be about trying out different models and even voting classifier. Like I said, so here in this one, we saw that the score reduced to 0.837, but my random forest classifier is already giving me a score of 0.849. So making use of voting classifier actually ended up reducing my score. So this way there is always that chance. Even if I use this, even if I take very good models and combine them, it's not guaranteed that voting classifier will do better. So there's a good chance that its score is going to be lesser than one of the models that are there within it. The only hope is that it will generalize better. So overall on unseen data, it might tend to do better because it is taking the opinion of these different classes of models. Apart from that, you just have to keep trying different models and see what works. Okay, so that is for voting classifier. But in general, with these tabular kind of data, the model that we'll be covering next week is boosting. So this boosting, or rather in the next session on Thursday, is boosting. And in general, boosting methods are known to give some of the best scores. And now maybe I can just run it, but the problem with boosting is that it always tends to overfit the data. Let's try it. The biggest problem is to do hyperparameter tuning in this and prevent overfitting. So let's see if it overfits this time. Okay, as you can see, it actually did end up giving a higher score, right? So it is the highest of what we have obtained so far. Random forest was 0.849. AdaBoost has ended up giving 0.856. So this way, with practice, you tend to know that some models tend to do very well. These boosting models are, in general, known to do very well with this tabular data. So again, there are variants like LightGBM and XGBoost, which tend to do even better. But as I said, the challenge is hyperparametric tuning and to ensure that they don't overfit. Okay. Yeah. So any other questions? All right. So in that case, we'll resume this week's content again on Thursday, wherein we'll cover the boosting-based models. And as I mentioned, the next week will be the, I think, the last session on these supervised learning models. And at least it will be the last session I'll take on this particular data set. So I want at least one or two of you to work on this data set and prepare a nice notebook. It's not that you have to try out a lot of things, but we'll try and understand how an end-to-end model is built. So just do the bare minimum efforts to start working on this data set. Even if you struggle to build a model, it is fine. We'll walk through the code together and build one good notebook wherein we try multiple different methods and see how we can analyze and do good work. Okay. So I want at least a couple of you to take this initiative and try out this competition. So this is the rainfall prediction competition on Kaggle. It's the current playground competition. Okay.
Sir, voting is explicitly used for classification, right?
No, there is voting regressor as well. What we have seen is voting classifier. If I come here, so there is a voting regressor. So in voting regressor also, it is going to work something like that. It is going to take the vote of the values of the different guys and then make a prediction. So if say this time it is going to be like continuous values, say maybe something like 150, 200, 350 or so on. It just averages all these predictions and then gives a prediction. So it is the same. It is just that how we would work for regression models. Now we are taking a vote on the prediction of regression models. So I think there is some confusions around these. So next week I'll just take a simple example which we can first understand through pen and paper, and then we'll see the code.
And stacking also has both classifier and regressor.
Yeah. Stacking in general is used. We use it in terms of stacking classifier, but there is no this to not use it for regressor. So it is the same thing. You can try out these different things here. So in stacking classifier, there is a meta estimator. Okay, it is now called final estimator, wherein you stack different classifiers, and then on top of that, you once again use a final estimator. If you all are interested, I can cover this in the next session as well. Otherwise, I don't think it's there in the lectures, but I could cover it. Okay. Any other questions? All right, then. Thank you for joining this week. And as I mentioned, do try out this data set and put in some effort from your side. And next week, next session, we'll build an end-to-end model and while trying out all these different. Okay. Thank you for joining.
Thank you, sir.
Thank you, sir.
Thank you, sir.